Right. Okay, let me move this. Thank you very much. So I'm Nazeem Edwards. I'm at Stellenbosch University in South Africa. My presentation is examining the intellectual quality of pre-service science teachers' classroom pedagogy. Okay, and so this is a case study. Let me just navigate this thing. Oh, there we go. So that is actually a picture of my building where I work. Okay, I'm on the 4th floor upstairs. So my presentation, I'm going to give you a brief overview. I'll give you a brief background in terms of the theory that I use. Then what is the purpose of the study, as well as the method used, results and findings, and in a brief discussion and conclusion. So first of all, I'm a science teacher educator. So one of the things that we're doing in what we call the postgraduate certificate of education program is we use what's known as the Productive Pedagogies. This was started in Australia many years ago. We kind of adopted this framework. So there are 4 dimensions which apply, and these are intellectual quality, connectedness, a supportive classroom environment, and working with and valuing difference. So in this study, I will merely focus on the intellectual quality aspect of this particular framework. Now, the dimension of intellectual quality looks at higher order thinking and the ability of students to manipulate information and ideas, through synthesis, explanation, or interpretation. Sorry. So the intellectual quality also refers to ensuring that the teacher is setting high expectations and a culture of inquiry in the classroom. Now, this is also linked to what we call the social cultural view of learning, which basically says that the individual learns from the social environment, be it his teacher, his parents, and so on. And language obviously also plays a very important part in this. Now, in terms of the Productive Pedagogies framework, it has been argued that this sort of works hand in hand with what we call the socio-cultural view of learning. Now, in science teacher education, the pedagogies that prospective science teachers appropriate are shaped within social settings. So my focus as a science educator, teacher educator, is to try to promote a culture of inquiry in the science classroom by focusing on the key concepts that underpin the curriculum. So let me give you an example. Here you see what we call a redox reaction. So what I do is I demonstrate to my students a practical aspect of a redox reaction, say, for example, by immersing a nail into a solution of copper sulfate. Now, a nail, as you know, is actually iron. So the iron reacts with the copper sulfate, but in the process, there's actually a redox reaction that takes place. So to let the student understand, one obviously needs to explain, but that explanation would normally take place at a micro level. So I use then a simulation, something similar to what's on the right-hand side of the picture. So now this is a key point for the students obviously to understand what a redox reaction is by examining actually what happens at the micro level. And so hopefully they develop their understanding better in that particular way. So the research questions that I'd like to answer are the following. Do pre-service science teachers focus on a small number of key concepts and relationships between and among concepts, or do the tasks that they set require deep or superficial understanding? And thirdly, to what extent are students engaged in thinking that requires them to apply, to analyze, to synthesize, and to evaluate knowledge? Now, this is what I call a qualitative study, a case study. And it consists of a small group, a sample group of 11 pre-service science teachers at my university. So we did video recordings of the lessons that they presented, and these were analyzed. So some of the physics lessons that were presented, for example, there was one on, well, there were actually 4 on equations of motion or motion in general. And so the example on the right would be the kinds of equations that the students would need to use to solve problems. Then there's Newton's laws of motion. A good example particularly would be Newton's second law of motion. And a third example would be Coulomb's law. And this is actually what students presented, and where they use the formula. I think it's very small on the right-hand side, but just to give you an idea. So then, as far as the chemistry lessons go, they did something, for example, on the atomic model. There's an illustration of that. They looked at physical and chemical change, and as well as phases of matter. Now, in terms of the findings which I analyzed from the data, what we found is that, for example, when students present Newton's second law, right, they use a simulation, and that is the simulation they use. And then they generate data, and they generate the graphs that go with it. Now, from this, one can clearly see, you know, I think in mathematics as well, we use multiple representations, be it graphical or numerical symbols, etc., to represent the various concepts. So this is what the students actually did, one of the students. In terms of someone presenting on the refraction, again, they used the simulation, and they spoke about Snell's law. A third example of Coulomb's law, that is the problem there, for example, so where a student was discussing Coulomb's law, using the formula, but noting the importance of the units in solving the problem. Excuse me. As far as the chemistry goes, they were very basic kind of presentations. Like the atomic model was presented by one of the students. And there's one on the decomposition of hydrogen peroxide. Okay, excuse me. Now, what I found was that, excuse me, that the physics lessons promoted deep understanding because it focused on the relationships between the concepts, and the students were required to engage in higher order thinking, such as using inverse proportionality. And the lessons also required application and analysis in the process of building their knowledge. as far as the chemistry lessons were concerned, they were very basic lessons where they sort of tapped into their prior knowledge of atomic structure and phases of matter. But none of these lessons actually required higher order thinking. So in conclusion, I want to say that my analysis shows that the physics lessons were generally more cognitively demanding and required higher order thinking, and it promoted a deeper understanding of the concepts, whereas the chemistry lessons were not as cognitively demanding and did not promote a deeper understanding of the concepts. So, but it could be, however, I would say, I'd like to add that the nature of the chemistry lessons perhaps required more recall of information, and perhaps the physics lessons lent itself, to the students being able to use more deep understanding and doing things of a higher order. So one of the recommendations that I would say I need to look at perhaps is to look at more lessons over a longer periods. For example, when the students go out to do their teaching practice. I think that is it from me. Thank you very much. Okay.